Okay, the next thing we need to discuss here are important features of function graphs. And when it comes to important features of function graphs, we're talking mainly about maximums and minimums. For instance, back in section 12, when we talked about parabolas, we talked about the fact that a parabola's vertex is either a minimum point, could also be a maximum point. Of course, other graphs may have minimums and maximums. This graph right here might have what's known as a local or relative maximum or a relative minimum here. That's mainly what we're going to talk about here. Of course, the other really important feature of a function graph is x-intercepts or zeros, which we have discussed previously. Again, that was mostly in section 12, the quadratic section. We went into pretty nauseating detail about zeros and x-intercepts. We will talk about a few other features that may show up on the test, but again, mostly we're just going to sort of review what we've talked about in terms of maximums, minimums, and x-intercepts. Some of the other features that we will talk about, I just mentioned, a relative or local minimum, minimum or maximum. We have not seen those show up on any official released SATs. That doesn't mean that they will never show up. We have seen those features, those graph features, in some of College Board's official materials, just not on official released tests. So just because we haven't seen any questions regarding those particular features show up on released tests doesn't mean we won't in the future. Let's actually add, right off the bat, we're going to add a couple of concepts or a couple of features to the mix here, increasing and decreasing intervals. So on example 11, let's run through each of these important features. So all we're going to do here is we're going to be placing and labeling some points at the different important features. So example 11a here, first of all, they tell us that this is the complete graph of the function f. So the graph just goes from here to here. So we are not to assume that this is going to keep going this way or keep going this way or even come down and go back up. This is the complete graph. So we have everything we need here. We need to place and label point A at the maximum value of f. And of course, that is here. By the way, you can pause the video and run through these on your own. Most students should be fine with these. So there is the maximum value of f. Do keep in mind, we've talked about this several times in previous function videos, that when we talk about value of f, remember that that is synonymous with the f of x value. It is also synonymous with the y value. So when we talk about the value of a function, we're just talking about the y when the function is graphed on the xy plane. We're talking about the y coordinate. So the greatest y coordinate would be here at that maximum point of f, the maximum value of f. The minimum, we're going to do point B at the minimum. There's the minimum value of f right there. Place and label points C and D at the x-intercepts. Well, that's easy. X-intercepts just means where the function hits the x-axis. This function hits the x-axis at 2 points there and there. So those will be points C and D, the x-intercepts. The example here, 11c, goes on to ask, determine the value of f at these points. Well, remember, the value of f is synonymous with value of y. And extremely important to remember, to know, to understand that when we are on the x-axis, the value of y is always 0. In fact, we've said this in other parts of the manual, the x-axis's equation is y equals 0. The y-axis's equation is x equals 0. So again, at these points, whatever the x value is, the y coordinate is going to be 0. So there's going to be some x value and then a 0 in the y position, and same thing here, there's going to be some x value and a 0 in the y position, and whatever that x value is and whatever that x value is, those are known as the zeros of the function, the x values that produce a y value of 0. So the determine the value of f at these points, the value of f at these points is 0. In example 11D, now we are doing the y-intercept, and of course the y-intercept is where the function hits the y-axis, the vertical axis. So it is that point right there. We are going to call that point E. That's what we are told to do here. That's the y-intercept, and the value of x at that point, again, that's got to be 0. If we are on the y-axis, then our x-coordinate is 0, x equals 0 on the y-axis, and therefore the value of x at that point is 0. And on which interval n or p is f, the function only decreasing. Okay, so this should be hopefully pretty obvious. We should be able to see that on interval p, the value of f is decreasing as our x values go up. In other words, as we move from left to right along the x-axis, we go from that x to that x to that x to that x, our y value is decreasing. We're going from this y to this y to this y to this y. So that's what happens in a decreasing function, that as x increases, y or f of x decreases. Now, this, of course, is not a fully decreasing function. A line going down like that might be a completely decreasing function. A line going up like that might be a completely increasing function. A parabola always has sort of one half of the parabola that is decreasing and one half that is increasing. This function decreases, then increases, then decreases again, and actually looks like it increases a little bit at the end. But anyway, in terms of example 11E, they are asking us on which labeled interval n or p is this function only decreasing, and of course that is interval p. On interval p, this function is decreasing. The y values are going down as the x values go up. And then, of course, for example 11f, they are asking us on which labeled interval n or p is f only increasing, and that is going to be interval n. We can see that as we move from left to right along the x-axis, our y values are getting bigger. They are increasing. So this is an increasing interval. So on interval n, f is only increasing. Over here is a really quick, simple hint in terms of increasing and decreasing. Again, it should be fairly intuitive, but just think of increasing as the graph is going up and decreasing is the graph is going down. That's the easiest way to think of it. Down at the bottom, again, mentioned a moment ago that there is a very distant possibility that you will see something other than absolute or global maximums or minimums. So the difference between an absolute global maximum minimum and a local relative maximum or minimum is this. So for instance, if you look at point A and point C, they both look like minimums. They both occur at the bottom of one of these turns. But you can see obviously C has a lower y value than A. So what we might say is that A is a minimum, but only for a certain interval. For instance, if I were to say, I don't know, let's make an interval. Let's say from whatever this x value is to this x value, A is a minimum for that interval. Is A the minimum for the entire function? Is it the absolute or global minimum? No, that would be C. But A is a minimum for a particular interval on this function, and therefore what we would call A is a local or relative minimum. It is a local minimum because in this local area, A is a minimum. Of course, if we consider the entire function, then C is going to be the global or absolute minimum. So again, A is a minimum for a certain, let's say, range of x values, but C is the quote-unquote real minimum. And then with B is also going to be a local relative, although this one's going to be a maximum. And that is because this function actually does not have an absolute maximum, and we can see that that's true because of these arrows. These arrows mean that this function will jet off to infinity, and therefore B is not going to be the absolute maximum, but it will be a local or relative maximum. And for this note, we are actually going to write down this function has no absolute / global max. This function just, like I said, goes off to infinity. Now, it is possible that, maybe there's other terms up here and there's some other relative maximums and minimums, but globally or absolutely, there is no maximum to this function, since this function, again, jets off to infinity. At the top of the next page, we have to talk a little bit about function graphs at the x-axis, do a little review of zeros, intercepts, and factors. Again, we spent a lot of time on this in section 12, the quadratic section. If you have not reviewed that section, if you've not done that section, you may want to do that section before you do this. Zeros, as we said many times in section 12, are very important on this test. It is very important to understand the relationship between zeros, intercepts, and factors. Actually, I'll do a little example right now. If we are told that x equals 3 is a 0, remember what that means is that that is an x value that will produce a y value of 0. So x equals 3 means that, x equals 3 is a 0, means that f of 3 equals 0. That also means, and we talked about this earlier in functions, that's an x value, that's a y value. It also means that 3, 0 is on the graph, and indeed that is the x-intercept, or at least one of the x-intercepts. We also talked about the fact that if we know that x equals 3 is a 0, that we know x minus 3 is a factor. So back in section 12, we talked about this chain of relationships, going from a given 0 value to an x-intercept to a factor. Very important that you're able to do this quickly and confidently and nimbly. What we are talking about here are those cases where we need to determine, usually we'll be given a graph, and we will need to determine from that graph something about the factors, something about the zeros. Very frequently what we're going to see when this particular aspect of key features of function graphs is being tested, we will often get a curve, sometimes a really bumpy one, and the curve is going to touch or cross the x-axis at several points. And we need to know a little bit about, as I just said, the relationship between zeros and factors, but we also need to know a little bit about how the exponent on a linear factor is going to affect the behavior of the function's graph at the x-axis. So let's jump into this. So if we have a factor of x minus n, we know, so, if I say there's a factor of x minus 3, like we were just saying at the top of the page, we know that x equals 3 is a 0. We went in this direction a moment ago, but now we're going in this direction. So again, if we have a factor of x minus 3, we know that x equals 3 is a 0, and we also know that 3, 0 is an x-intercept. So again, that's a factor, that's a 0, that's an x-intercept, but these are pretty much synonymous terms. So that's all that's being said here. If we have a factor of x minus n, that means that we have a 0 at x equals n, and it means that we have an x-intercept at n, 0. Now, what we need to add into the mix here is some information about this k. And what we need to know about that k is that if k is odd, so for instance, if I just have x minus 3 to the first, or x minus 3 to the third, or x minus 3 to the fifth, if k is odd, if that exponent on the linear factor is odd, what we will see on the graph of the function is we will see the graph going through the x-axis. So we're going to write down here, after if k is odd, we're going to write down graph crosses / goes through the x-axis at the 0, at x equals n. N is the 0. So again, if I had something like x minus 3 to the first, or x minus 3 to the third, what I would see at that 0, at x equals 3, at that point 3, 0, is I would see the graph going through, so let's say 3 is there, I would see the graph going through the axis. It would hit the axis at that point and then go through, versus the case where k is even. So if I had x minus 3 to the second, or to the fourth, or to the sixth, if k is even, the graph touches but does not cross In other words, I'll write this down here, is tangent to the x-axis at x equals n. So again, with the odd exponent, we said the graph will hit at x equals 3 and then go through. With an even exponent on that x minus 3 factor, we might see something like this, where the graph comes down, touches the axis, and then goes back up, as we do sometimes in a parabola. In fact, we did learn in section 12 that when we have a parabola whose equation is something like y equals x minus 3 squared, that parabola is basically going to look like this. It's going to touch at x equals 3, and both halves of the parabola are just going to go up from that point. So we will have a parabola that is tangent to the axis. It will not go through the axis. It will just touch it. So that is the relationship between the exponent on the linear factor and whether that exponent is odd or even. If the exponent is odd, the graph will go through the axis. If the exponent is even, the graph will touch the axis. Now, in terms of the relative size of k, in terms of the relative size of that exponent, we need to know, and I'm going to highlight this, this got lost here a little bit, that the higher the value of k, the more the curve will flatten out, the more time the curve will spend hovering around the axis at the 0. So again, if we have a factor of x minus n, and we already know that means that there's going to be a 0 at x equals n, but here we have that x minus n cubed. Here we have that x minus n to the first. X minus n to the first, you can see it just almost just looks like a line here, and it goes straight through. But x minus n cubed, you notice that we come up, we flatten out. The curve is spending a lot of time near the x-axis, and then it goes up through. That is an odd exponent, so the curve is going to go through the axis at x equals n. But because this 3 is larger than this 1, because this k value is larger than this k value, the cubed factor, again, it's going to make the curve flatten out a lot more near the x-axis. Same thing with the even exponents. Again, remember, even exponents don't cross, they're just tangent to, so we can see both on this black curve that has that 2 exponent on the factor and that gray curve that has the 4 exponent on the factor. They both come down, touch at x equals n, and then go back up. They're both tangent, but the factor here that has the exponent of 4, larger than the exponent here of 2, that gray curve is flattening out more near the axis than the black curve is. So again, odd versus even makes the graph cross versus touch, and then the larger the value of k, the more the graph flattens out around the axis. Let's take a look at how this is going to work. This question is similar to what you might see when College Board decides to test this particular concept. If you want to try this on your own, by all means, go ahead and do so. In example 12, we've got this funky graph. Again, we said this is very frequently what graphs will look like when College Board is testing this concept. A lot of bumps and turns on this graph. We have got that this is the function f, and y equals f of x. Okay, fine, that's standard stuff for function graphing questions. If f is defined as f of x equals x minus a squared, blah, 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 blah. So determine the following. So here's the way that I would go about doing a question like this. So the first thing that I would do is, I would not erase what I just wrote. I would identify the intercepts, the x-intercepts. So intercepts, x-intercepts. So what are my intercepts? My intercepts are going to be x equals -2. My next intercept is going to be x equals 1. And that last intercept there looks like it's going to be x equals 3. That's the first thing that I would do. The next thing that I would do is I would probably, and keep in mind, just very simple jump here, that obviously these 3 points are -2, 1, 0, and 3, 0. Then what I would do is I would get my factors. So I know that if, remember we said if x equals n is a 0, then x minus n is a factor. So if x equals -2, then x minus -2 is a factor, which means one of my factors is x plus 2. Another factor is going to be x minus 1. That's from the 0 here, this x equals 1, 0. And another one's going to be x minus 3. So those are going to be my three factors here. And from that point, I probably can start looking at the exponents. And what I mean by that is I can see that at this 0 here, which corresponds to this factor, I'm touching, I'm not going through, I'm not crossing, I'm just touching, I'm tangent to, which means the exponent on this factor needs to be even. We said that when the exponent on a linear factor is even, the graph will just touch the axis. These two zeros, we can see that the graph is going through, is crossing the x-axis at those two zeros. That means that for the x minus 1 and the x minus 3 both, we are going to have odd exponents, odd and odd. And that sort of sets us up here to start relating the three factors that we are given here to the three factors that we have just determined. So for instance, we should be able to see that there's only one even exponent on these factors here. The other two are odd. And in this case, we already have an even right here, which means that these two must be the odd, and this one right here must be the even, which means we've now figured out what a is. If x minus a is this factor, keep in mind that x plus 2 is the same as x minus -2, and therefore a must equal that -2. I'm just playing a little game of matchup there. X minus -2, x minus a. So a has to be that -2. A is, in other words, that 0. So the value of a must be -2. Again, only possible thing that a could be, because this is the only factor that has the even exponent. That matches up with this factor here. These other two factors must have odd exponents there and there. So I know the value of a must be -2. In terms of 12b here, if m and n are positive odd, okay, so that confirms what we were just doing. They are positive odd integers, and n is greater than m. What must be the value of b? Okay, so here you can, from the ingredients in the question, we can tell that we're being tested on the relative size of these exponents, which goes back to the rule that we were just talking about in terms of those k values. The higher the value of k, the more the curve flattens out. So let's see, the curve flattens out more here than it does here. What that means is that the exponent on this linear factor, which is that x minus 1, that odd exponent must be greater than the odd exponent on this linear factor. So let's do this. We know that the exponent on this guy has to be greater than the exponent on this guy. Well, they tell us that n is greater than m. So what that means is that the n must be the exponent on the x minus 1, and the m must be the exponent on the x minus 3. Again, this odd number had to be greater than this odd number. They tell us that n has to be greater than m. That means that the n must correspond to the exponent on the x minus 1 factor, and the m must correspond to the exponent on the x minus 3 factor. So what's going on here with these last two factors is that x minus c with the n exponent, that must be the x minus 1. So really we're just doing this. X minus 3, that's got to have the m exponent, and then x minus 1, that's got to have the n exponent. Now keep in mind, we don't know what m and n are, but it's not necessary to know what m and n are. All that's being tested here is the relative size of m and n, and that will be the case on a lot of these questions. You won't necessarily need to know what those exponents are. Now that we know that x minus b with the m exponent and x minus c with the n exponent, now that we have all that matched up, we should be able to see that the b has to be that 3. The b has to be 3, and that's what they were asking us. What must be the value of b? It's 3. Look, some of this stuff I guess can be slightly intimidating at first. Fortunately, these questions do not show up all that commonly. When they do, though, if you remember the rule about the even and odd exponent on the linear factor and the fact that the graph flattens out a little bit more the higher those exponents get, these questions shouldn't be all that difficult. At the top of the next page, we've got to talk about symmetry, although we're not really going to talk about symmetry because, as I've said several times, we talked about symmetry back in section 12, and often symmetry will be tested with regard to parabolas, which is exactly what we were talking about back in section 12. In terms of end behavior of graphs, for those of you that have taken probably mostly pre-calc, you almost certainly have dealt with end behavior of graphs. So what we need to know about end behavior, or I probably should say what might be nice to know about end behavior, because again, there have not been many, if any, questions that have required that you know about end behavior. Again, it's something that might come in handy on certain questions. It's something that might be tested in the future. So in terms of end behavior, so here's what we've got. We've got a polynomial function right there. The leading coefficient is that a sub n right there, and that leading coefficient is in front of the x term with the highest degree. So this is a polynomial of degree n. So for instance, in a quadratic, let's say 2x squared plus 3x minus 5. So that would be our a sub n. This would be the n exponent. A quadratic is obviously a polynomial of degree 2. So again, there's the degree of the function. And there's what we call the leading coefficient. And end behavior will depend on those two things. It will depend on the leading coefficient and the degree of the function. So if the degree of the function is even, let's start with the even function. So we're talking about quadratics, quartics, so, x squared, x to the fourth, x to the sixth. If your degree is even, first thing to know is that the two ends of the graph will always leave the graph in the relative to the x-axis in the same direction. In other words, the two ends of the graph will either both go up or they will both go down. The way that you know whether the two ends will go up or go down is by looking at the leading coefficient. If the leading coefficient is positive, in other words, if a sub n, this guy right here, this guy right here, if a sub n is positive, then the two ends of the graph will go shoot off to infinity in the first and second quadrants, and if a sub n, the leading coefficient, is negative, then we are going to have the graph shooting off to negative infinity down there in the third and fourth quadrant. So again, the two ends of the graph will leave the graph on the same side of the x-axis, both up or both down, and whether they go up or down will depend upon the leading coefficient's value. Positive, they'll both go up. Negative, they'll both go down. Now when it comes to a degree polynomial with a degree that is odd, so again, we're talking about linear functions, maybe cubic functions, I guess that would be called quintic functions, something like that. These two ends of the graph will actually leave the xy coordinate plane at opposite ends. One will go up, one will go down, and whether you have the graph going down to infinity in the third quadrant and up to negative infinity, and positive infinity, whether you have your graph going down to negative infinity in the third quadrant or in the second quadrant will again depend on the leading coefficient. If your leading coefficient is positive, then the graph is going to go to negative infinity down there in the third quadrant and positive infinity up there in the first quadrant. And if that leading coefficient is negative, the situation will be flipped. You will be going off to positive infinity in the second quadrant and negative infinity in the fourth quadrant. But again, the ends of the graph will leave the xy coordinate plane in opposite directions, one up, one down, versus the even degree polynomials where they sort of leave together in the same direction. Now, you might be sitting here going, what do I do with all this information? Well, quite honestly, if you're really looking for very highest possible scores, upper 700s all the way up to 800, you probably should just have this stuff memorized. Some of you probably already have this stuff memorized anyway. There is a note over here about turning points. I'm not going to go into too much detail on it. If you want to pause the video and read that, some of you will have already learned this. Again, if you've taken pre-calculus, you've almost certainly learned this. It just has to do with the relationship between the degree of a polynomial and the number of turning points, that a graph has. So for instance, there's a turning point there, TP. There's a turning point there, so this graph has 2 turning points. So that note over there just talks about how you can relate the degree of a polynomial to the number of turning points. There is a small possibility that you're going to see a question that deals with asymptotes. Main thing to know about asymptotes, vertical asymptotes at least, you almost certainly will not see a question that involves horizontal asymptotes on the SAT. You may see questions like that on the ACT, but probably not the SAT. Main thing to know about a vertical asymptote, in fact, I will write this down over here. Vertical asymptotes occur at x values that make the denominator of a function equal 0. When the denominator of a function equals 0, the function is undefined, and the value of x that produces that 0 in the denominator, the value of x that produces the undefined function, that value of x cannot be part of the domain of the function, and what you will end up seeing visually on a graph is you will end up seeing a vertical asymptote. So for instance, in this question, you can see that it appears that the 2 legs of the graph get very close to, but never seem to touch that vertical line at x equals -3. By the way, this question is simply asking which of the following functions could be represented by the graph. So that tells us that -3 is going to be an x value that makes the denominator of this function equal 0. And we can see that right there, if we throw in -3 for x, we will get 0. In other words, it is this denominator right here. I'm going to do this slightly different way. I'm going to set that denominator equal to 0, and then I'm going to subtract, and I get x equals -3. So it is that -3 value that will make this denominator equal 0, and therefore when x equals -3, the function in answer choice C will be undefined. And again, we said that when a function is undefined, because there's an x value that's making the denominator of the function equal 0, we will see a vertical asymptote at that x value. And that's indeed what we're seeing here on the graph, which means that the only possible answer here is C. None of these other answer choices, none of these other functions has a denominator that will be 0 when x equals -3. You should keep in mind that that point right there, 1, 0, that could help you. You could throw in, that's an x value, that's a y value. You could throw in 1 and 0 and see which of these answer choice functions works. However, I believe that both C and D will come out to 0. This one will be undefined. This one will be some fraction. This would be negative. When I throw in 1 for x, this will be -2/2, so that will just equal -1, which clearly doesn't work. So these two guys we would get rid of by throwing in the 1 and the 0, but then we'd be left between C and D, and at that point we'd pretty much have to use the information about asymptotes to do this question. So that is it for important features of function graphs. We will move on to do some transformations, translations in a moment. Make sure you review this stuff often. You will definitely see a few questions on every test that will revolve around this material.